Okay, so our next speaker is Dr. Rich Doyle. He's the Program Manager for Information and Data Science at the Jet Propulsion Laboratory in Pasadena. The scope of the office spans data science, autonomous systems, computing systems, software engineering, and a bunch of other things related to applying computer science principles to space exploration missions. He's also the project manager for the High Performance Spaceflight Computing Initiative, which is sponsored by NASA STMD, and they're collaborating with the Air Force Research Lab on this. He's got a long list of service in the AI intelligent systems communities, and quite pleased to have him here to present the changing role of computing in space. Thanks.
All right, thanks Josh and Michelle, and also Valerie, because I'm going to be building on some of the comments that you made in your presentation. All right, so we're going to be talking about how new ideas or different ideas about computing in space fold into the themes of this workshop, which is how to make better use of more and more data, and ultimately how data, computing, and networking all in the space context can all play together in useful ways. I do want to point out that one of my colleagues on the high performance spaceflight computing project, which I'll be describing in a bit of detail, that's Rafi Soam, and he's here in the room in the back. All right, so this is a little bit of just setting the context. I think everyone would agree, and certainly the themes of this workshop push hard towards the idea that we're going to need more computing in space in the most general sense. And the drivers for that are fairly well known. And in the NASA context, we have some unique requirements to think about when we are considering a next generation flight computer. The reality is we've been using the same flight computer for, it's either 15 or 20 years, or maybe even a bit beyond that, depending on whether you point to the time when the current workhorse flight computer called the RAD 750 was first deployed on space missions, or when the technology that it represents was actually frozen so that it could be deployed in space. So that's either 15 or 20 years old, depending on how you count that. So the case is fairly obvious that we need a next generation flight computer. And the drivers for that, in deep space, you never get the vehicle back. So it has to be ultra reliable, has to operate in very severe environments with temperature swings, perhaps radiation in the case of Jupiter. And increasingly, we want to support more and more autonomous operations. And that just goes with the general trend in exploration that we're pushing further and further into more operationally unknown, or at least uncertain, environments. And so that just ratchets the need for autonomy. Now, in the context of this workshop, we're going to be looking more at the science side of those questions. What form of onboard product generation, science product generation, in the onboard context is actually useful and value added as seen from a science perspective. But there's arguments for looking at scenarios in engineering as well. So Josh mentioned that we do have an investment underway in the NASA context called High Performance Spaceflight Computing, and we're partnered with the Air Force. So you don't have to think about it too much. The kinds of space-based missions that the Air Force and the DoD perform overlap in certain interests in terms of being able to process very high resolution image data, for example. So it's a very natural partnership between NASA and the DoD. So here's a very quick encapsulated history of the trends and advances in flight computing over many years. And the main trend there on the top goes through any number of both commercial chips and then towards the space-based chips, which you see here on the right. And the stair-step diagram on the bottom refers to the use of flight computing capability on different missions over the NASA history. So this, let me use the laser pointer here. Yeah, here. So we're going to be talking a bit about HPSC, which is a particular investment in next generation flight computing. But there's others that are emerging in this space, which are helping us look at more capable computing in a flight mission context. A few years back, when the HPSC project was just starting to get underway, we sat down with scientists, engineers, and mission designers, And we asked them to provide us with a set of use cases. You know, what are the actual drivers for the needs for a next generation flight computer? And as Valerie was saying, where you know, missions are designed for the obvious pragmatic reasons to sort of fit within a particular resource box, whether that's data storage, computing cycles, volume, power, all that. And if you're going to have a successful mission, it has to be sized to the resources available. But sometimes that gets you into a paradigm where people take a certain pride in being able to shoehorn amazing capability in a set of what are really impoverished resources. So when you give them the opportunity to open up their thinking, and maybe there's a message for this workshop too, you can see them actually struggle a bit, you know, to start thinking outside the box. They're so used to that shoehorning mode, and they're so very good at it, that you almost have to kick them a couple times before they really start thinking outside the box. So we saw that as these use cases were being developed, but we did kick them a bit, and they came up with a really excellent set. And in the NASA context, this spans both the kind of robotic science missions that JPL and also NASA Goddard are known for, as well as the human spaceflight missions, which are part of the NASA context. I'm not going to go through all of these, but you can actually see some interesting mappings between some of the use cases that show up on the human spaceflight side and on the science mission side. For example, the GN and C kind of maps onto entry, descent, and landing, and extreme terrain landing, proximity operations, and those kinds. So rather than go through this full list, I'm going to just pick one, and it's one that rather echoes some of Valerie's comments and points that she made. And this one is actually fairly mature. So we've known for some time that there are dust devils on the surface of Mars, very similar atmospheric phenomena, even though the atmospheric characteristics are quite different. But it's pretty much the same whirlwind type phenomena. So these were randomly captured by Spirit and Opportunity on the surface of Mars. It was a bit frustrating to the scientists because when these images came back, it was always after the fact because of the realities of light time delays and how data is prepared and processed and then made available for scrutiny by scientists on the ground. So the opportunity to actually study such a phenomenon in real time seemed to be not available because of light time and processing time delays. But we kind of put the lie to that with, again, something we'll be talking more about in this workshop, that if you create some software to put on board as a proxy to the scientist's interests, and that software can operate within whatever the available constraints are for computing, storage, and everything else, you can have a success, and it kind of puts the lie to the old assumption that you can't really study transient or short-lived phenomena behind a light time delay. With the right kind of software and computing support, and indeed you can. So what we've created, and this is actually fairly mature and fairly routine on the rovers these days, it's a combination of change detection, feature tracking capability, which can reliably capture dust devils as they occur. So now when the data product comes down for a scientist's interest and further scrutiny, that whole data product has been designed by the scientist. So it includes a video sequence, includes the tracking information, and a lot of ancillary information that is of direct interest to the scientist. So this kind of opens up the whole paradigm of what you might call science event detection and response, to have the remote system do something useful behind that light time delay, but very much directed and then embodied in software and computing by the scientist's interest, in a very direct fashion. So this is already a success story, and this is something that we can take inspiration from and keep building on. Okay, so now going back to that set of 19 use cases that I showed you on a previous chart. 19 is kind of a big number to get your head around. So what we did is we rolled them up into three broad categories, which are listed here. Actually, let me start with the one on the bottom, high data rate instruments. That's sort of an obvious one. And then this one here, vision-based algorithms, et cetera, that refers to a particular mission critical sequence, which I think has been made famous by the phrase 7 minutes of terror. This is the business of landing safely on the surface of Mars, 7 minutes from the top of the atmosphere to being on the surface. And rather famously, that all happens behind a light time delay, as the minimum is 20 minutes or so for back and forth transaction, and even longer than that depending on the configuration of Earth and Mars. So it has to be an autonomous sequence. Now, for landing on Mars, you're basically pulling out all the stops on not only your computing system, but the system in general. You want stringent fault tolerance, you're moving a lot of data, you're doing intense vision-based calculations, so you're stressing the whole system. That, up to the present time, that would become a design point, say, for the flight computing system, because if you didn't have your successful mission-critical sequence of landing on Mars, you don't have a mission. I'll unpack this a bit later. When we talk about HPSC, there's certain scalable capability involved, so that even though you need your computing to be in a particular configuration to land safely on Mars, you may never need that kind of intense, sustained computing capability once you're landed safely. And HPSC can be reconfigured to account for that, rather than you're stuck with this single design point, which kind of gets in the way for the rest of the mission. I mentioned drivers for autonomy. That all has to do with moving into more operationally unknown environments. By the way, Mars surface missions are probably the first great example of that. In the old days, we had orbiters, which once they had achieved orbit, and as we understood the basics of the orbital environment they were operating in, as well as internal state, that's about all we needed to model to have a successful operational mission. But once you're on the surface of a planet, interacting with that surface moment to moment, the game is very different. There's much more uncertainty that you have to manage for ongoing safety. And now we're pushing, looking at small bodies, comets, asteroids, so the operational uncertainty is being ratcheted up even more so. So that all leads to the view that we're going to need more capability for, call it engineering autonomy. And some of the AI and model-based reasoning capabilities fall into this category. But it turns out architecturally, they'll stress a flight computing system in different ways. Typically, search techniques are used here, and there's a different way of how you access and utilize memory, and how you need to do things like garbage collection. So it's very different. And so between these three different broad categories, which captured the set of 19 use cases, we pretty much understood that we needed to have a general purpose processor, which would cover this space. And we landed on a multi-core design, which is not astonishing because that's been available for commercial solutions for a long time. But it's just sort of inching its way into space. All right, so that's a roll-up of our broad set of flight computing drivers for next generation flight computing. I want to point to Rafi again. He did a very nice analysis where, it's one thing to have a set of use cases and kind of qualitative descriptions of the drivers for a next generation flight computing system, but we needed to start mapping that to something that looked like actual requirements. So Rafi got together a team and looked at that set of use cases again and mapped them to a set of canonical applications, which he ended up calling the Eigen Apps, with the idea that this is both a covering set and kind of incompressible for mapping the full space of flight computing capability that would be needed across those use cases. So without going into a lot of detail here, you can get a sense of the kind of analysis. But different needs of flight computing capacity, sometimes more emphasis on parallel algorithms, mission critical. Sometimes the use of more specialized co-processors. This is natural for certain payloads and instruments, for example. So we covered all that in this space. And this gave us a departing point for formally launching an investment between NASA and the Air Force, which is called the High Performance Spaceflight Computer. Without going too much into detail here, the basic idea is a dual quad-core configuration. There's some other specialized elements of the architecture having to do with the fault tolerance support and that kind of thing. But really what HPSC is about is 8 cores, which would be unprecedented in a flight computing system, and a lot of capability for both on-chip and off-chip communication, so that HPSC as a baseline capability can be extended in interesting ways. So for example, and I'll show you this in a moment in more detail, if you're not particularly power constrained, think of an Earth orbiter with large solar panels, then you might be happy to go beyond the 8-core configuration to a 16-core, 24-core, et cetera, as long as your power budget can manage that. So keeping that in mind, we work towards having HPSC be a very extensible architecture through the off-chip communication, so you can cascade or perhaps tile these processors together to get to whatever computing capacity makes sense for your mission. Along the same lines, there often will be need for more specialized coprocessors, whether these are graphic processing units are more and more interesting these days. FPGAs are another example, long established for use in space. And then there's emerging paradigms like neuromorphic processors, which we anticipate someday will find their way into space. HPSC has been built with this very open architecture so that you can configure it with specialized coprocessors of those types and others, to match the needs of your missions. All right, so here we are. What's another advantage of HPSC? Now, in space missions, this is true of maybe less of Earth orbiters, but more so for deep space. Power is always at a premium. So the 8-core configuration that I just described for HPSC, that was sized deliberately to match the power budget of the existing NASA workhorse flight computer, the RAD 750, which comes in at about 5 or 7 watts at the chip level. So HPSC in its baseline configuration of dual quad core or 8 cores comes in at the same power budget, but is about 2 orders of magnitude more capable. But the real point about HPSC, because of the ability to power scale, you literally turn cores on and off. The HPSC can actually cover an operating regime. It's not just a point solution when it comes to trading power and performance. So here's the HPSC 18-core chiplet, and but that's actually extensible or scalable in both directions. So if you want to go into power saving mode, you can turn it down to, say, 1 core operating and have a significantly less power usage than even the RAD 750 does today. If you're one of those solar orbiters that I mentioned, then you can go in the other direction up to a 16 core, even 24 core, and keep going. So the watchword here is flexibility, and that generally hasn't been available in a flight computer to date. So let me go back to a Mars scenario. So I mentioned that to land safely on Mars, you basically pull out all the stops. You push your ability to move data as quickly as possible. You're doing intense calculations using vision-based algorithms. And you're also pushing your fault tolerance to the limit. Now you've landed safely on Mars, and you're doing routine science operations. So perhaps you're never going to need that peak level of computing capability again, at least not in a sustained mode. It's also interesting to look at modes like nighttime operations on Mars, where maybe you're mostly quiescent, except for doing, say, infrared observations or what have you. This architecture that we've created under HPSC is very flexible, allow you to reconfigure to all these different modes of operating the flight computer according to the dynamic and evolving demands of the mission itself. So again, that hasn't been available prior. It's always been a single point solution design for flight computers. Okay, so there's my catchphrase there. Reinvent the role of computing in space. For those of you more interested in more specific quantitative objectives, these are the formal key performance parameters that have emerged in our high-performance spaceflight computing project. I was just talking about power scalability. I won't go through these in detail, but these are basically, talked about fault tolerance, extensibility. So we put quite a bit of thought into not only the capability, but the architecture of HPSC to make it be as broadly based, useful as possible. All right, let me just mention this partnership that we have, because there's so much interest in getting to a next generation solution for flight computing, not just within NASA, but also with our partners in DoD and the Air Force, that this project ends up having a number of different partners and is highly geographically distributed. For those of you who know the NASA context, there's 3 of the NASA centers are involved, JPL Goddard, but also JSC, and then we also have certain DoD entities and laboratories involved as well. So it's a bit of a complicated project to manage, but there's a lot of interest and will to go forward for getting to a better flight computing solution. In our near term, what we anticipate is that we will be finishing the development of HPSC as a chip, or a chiplet as we sometimes call it. And there are plans underway to actually deploy HPSC in concert with a different NASA technology investment, which is looking at next generation solutions for landing on planetary surfaces, and design a flight demonstration that would go on one of these. NASA has a new program involving industry, commercial lunar payload systems, and we're moving towards plans that would bring all this together so that we would actually do a flight demonstration of HPSC and the landing capability on one of these commercial lunar lander systems. So that hasn't been all fully played out yet as to where that's going to land on the schedule, but a few years from now, all goes well, we'll be actually demonstrating HPSC in this lunar context. But that's really just a start. We've been thinking about flight computing is kind of a technology amplifier. I mean, what mission isn't going to make good use of more capable flight computing? It's pretty much across the board. So rather than think about the deployment or the infusion of HPSC as kind of a case-by-case, one-off progression, we stepped back and look at the major mission application categories in the NASA context. And again, there's rather direct or obvious mappings between these as NASA interest applications and those of our partners with the DoD. So there's deep space, of course, and that's where it ratchets up the need for extreme reliability, operating as low power as possible, and generally operating in at least partly unknown environments. Surface systems, rovers, those will continue. Mars 2020 will be launched in July, all goes well. And I think NASA is just about to issue the public school naming contest that resulted in Sojourner, Spirit, Opportunity, Curiosity. So we still call it Mars 2020, not very excitingly, but there'll be a better name for that rover sometime soon. High data rate instruments, that's definitely relevant to what we'll be talking about here in the workshop. Valerie and I were noting just in chatting outside earlier that the HiRISE instrument, which is one of the ones she mentioned on Mars Reconnaissance Orbiter, effectively we use only something like 1% of its capacity because of the communication bottlenecks, the reality that. So what's really happening here is that there's these set of race conditions between these amazing sensors and instruments which have the ability to collect data at tremendous rates, and then being able to map that in some useful way to the other computing, storage, and of course communications, being able to get that data back to Earth. So thinking a little bit outside the box and looking ahead, if the reality today is we can only bring back about 1% of the data that HiRISE can collect, then is there some useful way to be computing on such data as it's being collected in a remote environment to generate intermediate data products that would be useful from a scientist perspective? And now let me jump all the way into the theme of this workshop, which is cloud computing, right? It's all about, can we push these increasingly familiar cloud services out into the solar system? Well, often there's a standard argument, and I've made it myself, that cloud computing is not going to be very relevant to deep space where you're behind a light time delay, because you're in an embedded situation and you just simply can't burst on demand into the cloud while you're behind a light time delay. So that seems almost definitive, but actually if you think about it in a more nuanced way, a better way to look at it is, could you be computing intermediate products in the onboard or remote context with the foreknowledge that eventually you'll be able to burst into the cloud? And so what form should those intermediate data products take to take full advantage of the cloud when it's available? If not on demand, it will be available at some point. That's a different way of thinking about, call it edge computing. And in the NASA context, we're really at the edge when we talk about edge computing. All right, so let's keep going. Human spaceflight. So this gets into different dynamics about human-machine interaction, direct support of the astronauts in terms of their access to knowledge bases, that kind of thing. And also the support of VR virtual reality and augmented reality techniques. Landing systems, we've talked about that. And then this last one, CubeSats and smallsats. We don't want to lose sight of that. We're seeing the tremendous possibilities with the advent of CubeSats and smallsats. It's been happening in Earth orbit for some time, and a little shout out to Marco, which won the CubeSat of the Year award recently, for the, showing the possibilities of CubeSats in a deep space or planetary context, again at Mars. So we're just starting to open up the thinking. And a nice way to think about CubeSats in deep space are these so-called mother-daughter architectures, where you can have smaller payloads attached to the landed system, which houses most of the capabilities. We're going to have I think rather famously, the Mars helicopter on the Mars 2020 mission. There's another example of that. So when we talk about computing and networking, say in a Mars or landed context, there's certainly some interesting scenarios to explore where, whether it's a helicopter or some other CubeSat-sized payload which goes away from the landed system but can remain in communication with it, then the possibilities for doing really interesting coordinated science or even just exploratory science just begin to explode. So we need to be looking at all of that. All right, within JPL, I'm going to point to Josh as well as Lucas here. And I don't know if Hiro Ono is in the room today, but the three of them, along with Rafi and I, are looking at the potential for how HPSC can support future Mars exploration. We'll be getting into this, I think, in breakouts, but at a rolled up level, Lucas is investigating scenarios where if you had the ability to be looking from orbit all the time, and there's certain phenomena which can be detected, say, through simple change detection techniques, such as the appearance of the possible evidence of water outbursts on crater walls. I think Lucas asked a question before that was kind of hinting in this direction. It's the paradigm where if you can look all the time and reliably be able to pick out the data which is going to be most interesting, and you can't possibly send all the data to the ground, so that can be done either with human eyes or with ground-based computing capabilities, then what are the possibilities for being able to reliably notice the water outbursts when they appear? It has to be supported with a flight computing or an onboard or a remote context, but it's all about supporting what the science objectives are. Hiro is looking at landed systems, both the very interesting questions about planning paths on the surface of Mars which preserve energy to the greatest extent, and also the paradigm that we sometimes call science while driving. Valerie had noticed a bottleneck between you can't be doing science when you need to communicate. Well, there's a different version of that for Mars rovers missions. Right now they're compute bound to the point where they're either driving from point A to point B or they're doing science, but they can't do both at the same time. They can't walk and chew gum at the same time, sometimes we put it. But more to the point, the joke is that while it's in traverse mode, the rover might just trundle right by the exposed dinosaur bone and never notice. Now, we're not really expecting to find dinosaur bones on Mars, but you get the point. So we're calling that science while driving, and computing is obviously one of the bottleneck resources that we're trying to alleviate. So that's what Hiro's up to. And then Josh, also very inspired, this is kind of the origin of the theme which landed on this workshop, which is looking at the combination of computing and networking in remote context, particularly Mars. All right, so you'll probably be hearing more about that as we go. Now I'm going to start a segue towards Les's presentation to follow, which will be looking at the communications aspects. But I'll just hit on one element, the so-called DTN paradigm, delay tolerant networking, and what are the possibilities for sharing computing and communication resources in a remote environment, given that things like DTN are becoming more and more mature. So there's Mars again. There's all kinds of scenarios, which we've been exploring already. But let me point to one on the engineering side. It's important to be constantly monitoring the health of your vehicles. And pretty much to date, we always think of space platforms, whether they're landed or orbiters, as they're self-contained resource envelopes, which in simple terms means the rover is responsible for its own health, just like the orbiter is responsible for its own health. But if you've got multiple assets in the Mars environment which can routinely communicate with each other, might it be better to have the engineering data that the rover's collecting be offloaded to an orbiter, which has spare cycles? The fault protection analysis is done there while the rover focuses on its main mission, which is perhaps the science while driving. Again, it explodes the possibilities when you can share computing cycles, share data, share communication possibilities. And that's in the Mars environment. The lunar environment is coming on strong, and there's lots of possibilities there. And what makes it more interesting is the dynamic having to do with the presence of crew members, astronauts, and the need for human-machine interactions, and always having the paramount human safety element there as well. Earth orbit. We haven't talked too much about Earth orbit, but because this workshop is themed to push out deeper into the solar system. But it's certainly relevant in an Earth observing context here. A gentleman earlier had asked about commercial data services. Now, obviously, that's already starting to happen in Earth orbit, and that's very exciting. But it starts to point to the challenges of how are you going to coordinate all that data. So you've got multiple, perhaps commercial-based data platforms operating continuously. Does that data just all need to go to the ground? Are there useful cross-links? What are the need to coordinate the platforms? Are they doing joint observations, or at least preparing the data such that you can do analysis across different observables? And how does that all get coordinated, and what's the role of data standards? There's a lot of interesting questions in there. So that's starting to happen in Earth orbit. Now, I don't know if the point of the question was, might we once someday see commercial data collection interests at the Moon and Mars? Well, I think it's inevitable. I don't know what that's happening quite in the near term, but it's something we can be thinking about in this workshop, that the data collection capability might also be commercially based as we push farther out into the solar system. Okay, I think I'm just about on time here, and I got one more chart. Okay, so this is my get off the stage chart. Let me just say a few words, and then we'll open it up for questions. One of the challenges in thinking about pushing something like cloud services out into deep space is just the scale of the space that we're dealing with, and our ability to meaningfully have multiple assets not only deployed but sustained in different planetary environments. It's been noted already several times that has reached quite a mature level in the Mars environment, and and we expect that to continue. So we have enough simultaneously operating assets at Mars that we can talk routinely about doing data relays and some of the other scenarios about sharing commodity type services across the Martian environment routinely. I think we're going to be starting to see that at the Moon as well, and obviously it's happening on Earth. So Jupiter with Europa, Saturn with Enceladus, these are amazingly interesting places that we want to investigate, and there are concepts for more missions to investigate those two intriguing ice worlds in the solar system. But it kind of begs the question, what would it take to have multiple assets operating simultaneously, but also in a sustained fashion when we're talking about Jupiter, Saturn, and beyond? Just the difficulty of getting there. In the case of Jupiter, the difficulties of operating long-term in the radiation environment. So there's no good answer to those questions today. But within this workshop, we're going to be exploring all those possibilities and looking at all these ways of shifting paradigms that involve starting, as always, from the science questions and similar drivers, and then asking, can we recombine computing, networking, data storage in interesting ways to further those goals in highly flexible and also scalable ways, and perhaps come up with mission concepts that we've only been scratching at to date. So I'll leave this on here and turn to questions. Thank you.